And I'd now like to introduce Professor Michael Klein, who is very active in research, addressing problems from material science through to biology with computational modeling and phase behavior. He also is Dean at the College of Science and Technology at Temple University, following an equally glittering career at the University of Pennsylvania. And one little bit that isn't in the bio is he chaired the last review after Research Excellence Assessment in the UK on the study of chemistry, an international review, and it was so successful that afterwards EPSRC stopped doing it. They claimed it was too expensive, but I think it was very penetrating review. Thank you, Michael. The title of his talk is New Perspectives on Modeling Water and Macromolecules.
So good, thank you, Andrew. Good morning, everybody. Enormous pleasure to be back here in the Emirates and talk to you a little bit about science. I'm going to use most of my time to talk about context of science, my life in science, because I think there are lessons to be learned from the young people in the audience, and more I see that as my role to try and inspire young people to get into science. Certainly in North America, the study of science seems to have lost its traction. At my university, we admitted about 1,000 students this academic year, and only 5 come to study physics, 9 come to study mathematics, and 20 came to study chemistry. So the core subjects that I was educated in as a student seem to be of no interest to, at least in the part of the US where I live. So hopefully I can inspire people about why, at least when I was young, I found science interesting. So my current personal inspiration is here. It's a Siamese cat by the name of Higgs boson. Okay, so why are we here? So Tony and I decided that we would come and investigate where we might hold this conference, and this was a shot that was taken from the hotel we were at last night, looking back at the hotel where we are now. I can't imagine anywhere on the planet better than this, but I'm open to have suggestions. Wonderful to be back in this part of the world, and in particular, would like to thank Sheikh Saud. We had the opening ceremony, but Sheikh Saud's vision for the way science and technology will impact the people here is an inspiration, and it is one of the reasons I've been coming here almost every year for the past 15 years. That's the title of my talk. You've seen that already. And I want to start, as I said, with some nostalgia. My own research has been heavily involved with the use of computers to model the properties of materials, but in general, I like to say if it moves, we can model it, at least within the inanimate world. I don't pretend to be able to model elephants moving. Anybody interested in more details of what I'm talking about, you can certainly find videos of my recent talks online. So let's start with some early years. So I was born in 1940 during the Blitz of London. Of course, I don't remember that because I was a baby. But I should tell you that my formative years were essentially dominated by these 2 giants of Western civilization, I would say, that saved us from the abyss. I grew up with high school with Winston Churchill as the Prime Minister, and certainly as an undergraduate at university, Eisenhower was the President of the United States. Is there anybody else in the room that was around at that time? So it's a very special beginning, I should tell people. But another thing that I'd like to share with people is I was living in London at the time. I was at grammar school, and I remember vividly when George VI died and Queen Elizabeth came to the throne. And as you know, last year, unfortunately, she died. And I witnessed the Great Smog of London in 1952. You'll notice the policeman there was already doing the prototype of the mask we all wore for 2 years. Or it's a kind of Hannibal Lecter, for any of you that saw that movie. Yeah, I vividly remember that. So that led to transformations in the use of coal to heat houses in the UK, but we won't talk about that. At the time I was in high school, massive changes happened in the world of science. Of course, I was not aware of them. I was too busy learning mathematics and other things. But there's a pioneering paper which really is the birth of biophysics by two gentlemen, Hodgkin and Huxley. Actually, this paper is more about Huxley than it is about Hodgkin. About the action potential. If I decide I want to move my arm, what are the signals? What are the fundamental processes that take place? And these gentlemen build an analog model of what is actually happened in the physiology of our bodies. To put it in context, we didn't even know that membrane proteins existed until 1972. So this world, these gentlemen 20 years before had an intuition of what was going on. I was fortunate to interact with both of these in my association with Cambridge University as a visitor to Cambridge University, and in particular Trinity College, because both of these gentlemen were the masters of Trinity College. When I first went, Andrew Huxley was the master, and he was succeeded by Huxley. Why were these gentlemen so important? Why did they get a Nobel Prize? Well, it goes back to work they did when they were young scientists. Hodgkin was the kind of thesis advisor of Huxley. Hodgkin was 25 years old and Huxley was 21. And young people in the room, pause for a moment and read the abstract of this paper. These guys never claimed they were the first to do anything, the last to do anything, the greatest discovery. Just read what they said. People think that action potential is due to some electrical signal. If we can put an electrode in axon, we should be able to measure this potential. And, well, they say, well, to get something we can actually put an electrode in, we've got to look. And they found, in fact, they did the work down on the south coast of England because they wanted to get hold of giant squids that they could work on. And one reference to the paper, well, that led to a Nobel Prize. This was 1939. And of course, there was the Second World War, so this work was postponed till the 1950s, which was paper 2 in this series. So first one, 1939, second one, 1952. Exciting time for science after the world came out of World War II, and this famous paper on the structures of DNA. Look at the picture of these guys at the time. Science is done by young people, not old people like me. Look. But 1953 was what changed my life, in a sense, what got me interested in science. I played less soccer in the street, less cricket. I decided to study books. I wasn't even sure that I could read when I was that age. But anyway, I was taken by my high school teacher to listen to a lecture by a guy that happened to get a Nobel Prize, probably the youngest that's ever won one, for the X-ray crystallography at the Royal Institution in London. I worked a bit harder in school, and the rest's history. 1953 was also the birth of computational science. The second computer of the modern type was delivered to Los Alamos Lab, and a group of very brilliant people did the first, what I would call statistical thermodynamics, on a large-scale fast computing machine, as they called it. The interesting thing for me about this paper is that the women were co-authors on the paper. It was the fashion at the time to thank the women that worked on the project in the acknowledgements rather than putting their names there. This paper we referred to, those of us in the field at the time, as the Metropolis method. And it turns out that it was about an algorithm for sampling using a computer, a Monte Carlo method. And I puzzled for years about An algorithm is not invented by a group. Somebody has this spark of idea. Who was it? It turns out that talking to the few people left in that were around or were descendants of these people, I think it's pretty clear that the author of this idea was, I'll show you on the next slide. I read the obituary of Ariana Rosenbluth, and it turned out it went into great detail about what she actually did. I mean, she died during COVID, not of COVID. But in the world in which I grew up, Bernie Alder claimed to have invented this method that we use, the Monte Carlo sampling method. In fact, I was at a meeting in 1985 where a bunch of us younger people at the time asked him what he actually did, and to those of us in the room was not convincing. But I went back and read the original papers, and the original paper does acknowledge discussions with Bernie Alder, in fact. But I think it was Ariana Rosenbluth. Perhaps at breakfast she discussed with her husband, Marshall Rosenbluth. I don't know, I wasn't there. But it's, I think, an interesting factoid. Another very important paper, because after the Second World War, neutron reactors, the scattering of neutrons turned out to be a very powerful tool. And this very influential paper, at least to me as a young scientist, it contained the generalization of the radial distribution function. If I'm in a liquid, I sit here, I ask what is the probability of finding another particle a distance r away. And this generalized this concept of structure to correlations in time and space, and how it's related to the Fourier transform of that in momentum transfer and energy transfer in a scattering event. So very important paper for me, anyway, as a young scientist. Also in the 50s, we had the structure of viruses, very topical right now. Rosalind Franklin published a paper in Nature in 1955. I guess we know the story of how her diffraction patterns influenced the people that did the structure of DNA. But she actually did the structure of helical virus capsid. Very important work. Unfortunately, she died in 1958. There's the famous diffraction pattern she took of DNA, which inspired Crick and Watson. 1958, when I went to university, Faraday Society discussion meeting contains two papers by the late Rosalind Franklin. They were written by Aaron Klug, not being around. I think phenomenal papers. There was the follow-up of her own work, which she didn't write up, but Aaron Klug did. And the thing that interested me, she's on a paper on the structure of Teflon, another helical structure. And it's a terrific paper, but I like to show this because they introduced the notion of disorder, that there's a helical structure to the fluorine atoms in the crystal, and as you heat it up, these chains can move up and down and rotate, and the idea of a screw disorder was introduced, and how this affects the diffuse scattering on the X-ray pattern. So the graphics then was kind of interesting. So the machine shop built this model to show how helical motion can occur. So computer graphics has evolved quite a lot since then, right? You had to go to the workshop, picture of a screwdriver. These papers are pretty ignored, actually, but they are phenomenal papers. And this discussion meeting, 1958, contains gems of science from liquid crystals and other materials. So I said I went to university in 1958, and one had to do a research project if you wanted a degree, an honors degree. And I asked the head of department whether I could do theory. And Douglas Everett, physical chemist, looked at me and he said, "Klein, chemists wear white lab coats." The concept of doing theory didn't exist, but I must have been very persuasive, because he assigned me a couple of papers to read and then come back and talk to him. So this was the paper that he assigned me number 1. It was by Bernal and Fowler on the theory of water and ionic solutions. It is still an incredibly important paper to read. These guys introduced the notion of a Lennard-Jones potential. And the interesting thing to me, when I started trying to do some calculations, I went to the literature and was looking how to do the infinite sum of a series of 1 over r to the n, to the power n. And there was a series of papers by Jones and Ingham. And then as I tracked through these papers, it suddenly, instead of Jones, there was an asterisk, it said Lennard-Jones, and it said formerly Jones. So in 1926, he got married to a woman with the last name Leonard, and he took the wife's name. Very, very interesting story. Don't know any more about it than that. Fabulous paper. I learned a lot from it, and has inspired my work since that time. The second group of papers that Douglas Everett asked me to read were by John Popel and Lennard-Jones and Popel. The titles are very interesting here. Popel wrote a paper on the structure of water, and largely ignored, actually, but beautiful paper. And we have Sir John Lennard-Jones and Popel with a discussion of lone pair electrons. Immensely fashionable right now. Ram Sardri from Santa Barbara, very interested in the role of lone pairs. So what goes around comes around. Very interesting papers to me. They're kind of latent in my brain from a long, long time ago. I won't say any more about Lennard-Jones. Anyway, I managed to stay on for a PhD. I tried to change from studying chemistry to physics. I got a scholarship from the DSIR in London to do a PhD, and I wanted to switch to do elementary particle physics. And I went to register in the physics department, and the bureaucrats in London said I had to repeat the final year of physics because my scholarship was given in chemistry. So I went back to chemistry to see Douglas Everett and said, I would like to do a PhD, but I would like to do physics in the chemistry department. So fortunately, Douglas was immensely helpful to me. So in fact, I think it was fortunate they didn't let me change to elementary particles, because I started a PhD, and the topic I was given was rare gas solids. So the discovery of the rare gases is one of the rare, if not unique, examples where the Nobel Prize in physics and chemistry was given to the one discovery. Were people aware of that? So anyway, that was, so what was my particular problem that I was given is, what is the role of zero-point energy in the properties of these simple materials? So that, I don't have time to go into what I actually did, but it meant that I had to study the properties of materials in general, a lot of things about intermolecular forces, about behavior of materials in general, elasticity theory, and very fortunate that my thesis advisor gave me 2 papers to read. They're cited in here. He gave me a review paper to read, and he sent me back to the original papers, Peter to buy. And then he went off on sabbatical. This was the best thing that happened to me, because there was no internet. I communicated by mail. The latency time with the reply was 6 to 8 weeks, and I wrote my first paper. Any young people in the room? Encourage your thesis advisor to go away. It was very productive for me. And I gave the results at a low-temperature physics conference, September 1962 in London. I got the offer of 2 postdoc positions. And I was a first-year graduate student. So I would really encourage people to try and become independent. So hard to imagine, but this was 60 years ago. My first paper came out, 60 years ago. Anyway, as a student, my advisor sent me to an international conference in Copenhagen. Phenomenal experience to be around people from the frontiers of the subject. Very influential for me was meeting some of these people. And also there was a companion summer school, which lectures were given by people here. Peter Debye was a lecturer. Walter Cohn was a lecturer. And during Cohn's lectures, I was sitting beside a guy called Lou Sham, who was a graduate student at Cambridge. And I listened to Honeberg-Cohn theory by Walter Cohn. Unimagined, really, but that was part of my life. And then phenomenal lectures on beta-saltpeter equations from David Thouless, who looked like he was 10 years old at the time. I don't know what his real age was. But anyway, so the summer school and the subsequent conference at Chalk River on many-body theory, that's the Canadian Nuclear Lab. The big topic was S of k and omega and G of r and t, and that inspired me to think about how I might be able to calculate these things. And I didn't get to do that because this fabulous scientist, Anisur Rahman, did it in October '64. The paper came out, and he had calculated G of r and t for a simple model of liquid argon. I just want to say a couple of words about Anisur Rahman because I did know Anis rather well. He died in 1987, but I did overlap with him and know him. I've come across these photographs of him. He was an undergraduate at Cambridge. He born in Hyderabad, grew up in Hyderabad from what must have been a wealthy Hindu family, but a Muslim family. And he went to Cambridge. He was at Downing College. And there's a photograph of him in 1949. He hitchhiked back from Cambridge to Hyderabad. He hitchhiked. There's a picture of him arriving home. His wife sent me that picture. A couple of pictures of him here. He died of cancer as a young man, unfortunately. So for the young people in the room, I was a postdoc in 3 different countries, and I got a job in a 4th country. So don't worry if it's tough to find a job, okay? Life as a scientist is tough. 3 different countries, and mostly in physics, even though I was a chemist by training, but finally I landed a job in Canada, fabulous, and able to start my independent career. When I got to Canada, I reconnected with brilliant Australian scientist, John Barker, who I'd corresponded with as a graduate student. And I had some technical problems with computing multidimensional integrals, and we exchanged correspondence. And I reunited with him. And he's the guy that did the first computer simulation of a molecule, I mean, water. And not cited very much, not recognized. It's unfortunate. It was a tremendous scientist. Never had a PhD, by the way. He did, as a lot of people did in that time, he did an honors degree in chemistry, physics, mathematics. Never got a PhD, but phenomenal man. This is the paper that's normally chosen as the one that the first simulation of a liquid, but it isn't, but as I just said, but very influential paper by Anisur Rahman and Frank Stillinger. I entered this field at about the same time as the Stillinger-Rahman paper came out. I did a Monte Carlo calculation, which was actually going back to my thesis, my PhD thesis, and using a computer rather than a calculator. And that paper came out in 1971, so 52 years ago. I collaborated with John Barker. I spent some time working with him at IBM research lab in California. It was very profitable for both of us, and in some sense did my PhD thesis many years later to complete what was my project. Got inspired to study S of K and omega on a computer with longtime friend and collaborator Jean-Pierre Hansen. Both of us, we met in 1970. Both of us were doing Monte Carlo calculations on big computers and decided together to try and do molecular dynamics. And I don't know if this paper's the world record. We did the work and submitted it 1972, at 73 by the time we submitted it. And somehow having trouble with referees, it didn't come out for 3 more years. Does anybody? So again, don't give up. We didn't really have competitors anywhere on the planet, so we weren't particularly in a hurry to get it published. But don't get depressed if your paper gets trashed. We had the confidence that it was actually good work, and eventually it did come out. As I said, submitted in 73, published in 76. So that's typical for a mathematician, by the way. Somebody else has to check the proof. I'm going to speed through some more modern things. So, as I say here, that to understand what happened in the 1980s, you need to understand what happened the decade before, to understand that the decade before, and so on. So I've taken you very rapidly up to a few years ago. So 1980s in my field, using computers to model things, was the age of algorithms rather than computers. Smart people developed incredible ways to do things. Hans Andersen at Stanford, Parnella Raman was born, Shuichi Noze, and all of these impacted, and then we had Carl Parnello, ab initio, MD, and so on. Hans Andersen, I think, is largely ignored, and is a hero of mine. He was interested in studying a glass on a computer and was worried about the fact that if you cool something, normally it shrinks. Of course, ice is the other way around, but normally the simulation cell would have to adapt. And he invented the method of extended Lagrangians, how you couple the shape of the simulation cell to the dynamical variables. Genius piece of work, massively cited. Parnello and Raman picked up on this in 1980. I was at a Gordon conference on liquid, and Anise came running over to me, waving a piece of paper. Mike, we just sent this in, and you've got to do this for molecules, which was very easy to say, but it took us another couple of years to do it for molecules, and our paper came out in PhysRev Letter, 1983, and I had 2 brilliant postdocs at the time in my group, and we called it Andersen, Parnella, Raman. Somehow, with the passage of time, Hans Andersen's been ignored. This is sad, because it's really his method. We applied this to molecules and don't have time. But the most important thing is this paper which I shared with Bill Jorgensen and others, where these methods were integrated into one paper, where the Andersen-Parnella-Raman was used as a check on the MPT Monte Carlo work that Bill Jorgensen had done. So massively cited paper, which really is redoing with modern tools the paper of Banal and Fowler, 1933. So it really took 50 years to do better than they did. And there's a picture of Bill. We actually went together to Wuhan, November 2019. So, and survived. So we applied these things to multiple examples. The last thing I want to mention is this real academic interest in using path integrals to put in nuclear quantum effects, which a group of us played with, but at the time I had another brilliant postdoc, Michiel Sprick. We used these things, and Anise and Michele also worked on these things. So I'm going to go faster now. 1985 saw the birth of ab initio MD, and mustn't let it go by without mentioning Stefano Baroni. Those of us that use quantum espresso, if you want to do these things, he's really the champion of that code. So there's a picture of me from that era with at Trinity College, and I spent quite a bit of time going backwards and forwards from North America to Cambridge. Great advances in algorithms, particularly for electronic structure, brings us into the 1990s. These ab initio MD was empowered with density functional theory, so we have to pay homage to my colleague John Perdue. The PBE paper has 165, I looked yesterday, 165,000 citations. It changes as you look at it. Should I say that again? 165. And this is another example for the young people in the room. The title of a paper is incredibly important because it is found by going to Google. Nobody's going to type in 3 lines title of a paper. Generalized gradient approximation made simple. Right, there you are. So you're going to put in, you'll find this paper. So 2000 was a seminal event. A group of us all met in Messina in Italy. Michele Paranello got an honorary degree. Walter Cohn was there. Unfortunately, he's not in this picture, but he was definitely there. In the modern world, these things have gone on and been used in biology. But the title of my paper was Water, and so John Perdue's come up with a scan functional, and a group of us, including Umesh, applied this and showed that it was very useful broadly, even for hydrogen bonded systems. So we have some papers on water. But then you can't publish a paper today if you're not using machine learning. And so the age of thinking and using brains has been supplanted by artificial intelligence. So this paper was silent for a while. Very important paper. And it took a few years to catch on, but now it's everywhere. And my friends at Princeton have issued software that people can use that enable us to extend density functional theory from hundreds of atoms to billions even, if you have a big enough computer. People in the UK have been involved and elsewhere. There's a whole series of applications. And Michele continues to go on inventing new algorithms that people use. And we have next generations of people doing phenomenal work. I hosted a meeting at my university has a campus in Rome, which is a beautiful place to have a meeting. So a couple of years, well, 3 years ago now, we had a meeting about machine learning and molecular simulation. Very inspirational to hear what are the possibilities of these tools. Great paper of Michele, I think, for young people, if they want to look at what's possible. This is using machine learning to model gallium, which is an interesting material because it has latent molecules that come together, dissociate, make diatomics, and so on, and did the phase diagram. And then this group at Princeton won the Gordon Bell Prize, showing that they could occupy a whole machine and look at dislocations move. And again, very inspirational material science. My group's been involved in applying these tools to water. Not got time to say too much about it, but I just want to end by saying that a couple of slides on this paper that came out celebrating 125 years of the Journal of Physical Chemistry. It got a cover on that. And we, in the title here, say we modeling liquid water by climbing up Jacob's ladder in density functional theory. So for those of you that are not familiar with Jacob's ladder, I made a copy, which I just stole off the web of William Blake's 1805 painting of Jacob's Ladder. And I would like to draw attention to this character here, who is Isaac Newton. And so is he coming down from heaven? So Blake was obsessed with Newton, so this is Blake's painting of Newton, which spans a period of 10 years. I think he was trying to make up his mind whether he actually liked Newton or not. And at the Tate Gallery, there's a plaque associated with this which said that actually William Blake didn't like Newton because he didn't like his reduction of science to of the beauty around, ignore the beauty of nature and worry about understanding analytically. So I leave you with this question here. Is Blake's Newton being expelled from heaven, or is he coming down to save us all? So that's it, really. So we have a whole slew of works coming out on water. You'll find them very easily if you Google. I don't have time to go into that, but I do want to highlight the brilliant young people involved in the work. Chunyi Zhang, who will soon be looking for an academic job, and my young colleague, Shifan Wu at Temple University. So I think I'm going to end there. There's lots more stuff on water, but don't have time to do that. So just end with, here we are. Thank you.
Thank you, Mike. You've earned one. Wasn't that fantastic? Are there any questions?
We should.
I've made a few comments that I would like to add if no one wants to ask any questions, but I'd love the audience to have a go first.
We should move on, Andrew.
No, no, we shouldn't. give them a chance to talk about heroes. Well, I would say, since Blake wrote the famous poem, Hymn Jerusalem, which talks about the return of the Messiah to earth, it was Newton returning to earth as a Messiah. There we go. That's my interpretation. Any other questions, comments?